people are going to be popping in, and I'm probably going to mute my video also. So here we are. So I'm not sharing my screen yet, but I will.
Not yet.
Okay. Okay. So are we good now?
Yes, sir.
Yeah.
Okay. All right. Sounds good. Well, thank you all for joining. So try to get to the point because I'm limiting this to exactly 1 hour. So I suppose since you're here, you all were able to join the course. Although there's some names I didn't see on it. But let's go to the course homepage. First of all, do you have any difficulties in navigating the course, or any difficulties in joining?
No, sir.
Okay. I know some people had trouble using the direct link. You can also join using this. Whoops, where'd it go? You can also join using this link here. And where is it? Yeah, you can use this link here and then the join code. Right, but presumably if you've all joined, that's not a problem. So let's go back to the syllabus page. All right. So the source of material for this class is, well, two sources. There's this summer packet, and then there's the abstract algebra textbook. Now, the summer packet contains material that's like college algebra level. This is like first year, second year college stuff, or even pre-cal. But I find that one of the major problems that students have is they really have not mastered pre-cal math. So I want to go back over that, make sure that you really have that solid. And this is a chance for you to do that. Also, there's some material in the abstract algebra content that you need to have some idea about already. So the two resources are here. The summer packet you can download, and the textbook you can download. Other resources include this playlist. I will be posting notes for this class, the notes that I do online here. And this is probably not that useful, but I have run this pre-class previously and I did some problems online. So that might be a resource. And then here's the answer key for the abstract algebra. The summer packet has answers at the end. Right. Now I do encourage you to use the answers correctly. I think some people try to do the problem and they do it hurriedly, and then they go look at the answer and then they correct their answers. Do the problem carefully, because you should be able to do the problem without the benefit of the answers. Right, so do the problem carefully, write it out systematically, and then check your answer. Don't think that if you can correct your answer that you understand how to do the problem. You should be able to do the problem without needing to rely on the answer first. Okay, so that's my little sermon. Well, let's look at the material that I'm doing today. So the first assignment is here. It is there. Let me go ahead and mute my video. That might help the bandwidth here. Sometimes I'm a little bit bandwidth challenged. I hope I haven't been cutting out or anything. Am I okay? Can anybody tell me, am I okay? Are you getting clear?
So far, so good.
So far, so good? All right, thank you. All right, so let's go back to the course. Not here, it must be here. Where am I? Okay, well, it's got to be here somewhere. So let's go back here. And let's look at some of these problems. So the first assignment was here. And right here. I think that's the only assignment you see so far. And let me hide this. this. Okay. All right. So this is here. So these are all problems from the summer packet, and we'll look at some of these. Most is algebraic manipulation. As I said, very important. And then here we have some problems that cover the basic material, abstract algebra material. The topic here, these are all having to do with complex numbers, complex arithmetic. And there's two ways to do complex arithmetic. You can use rectangular form, which is a plus bi, or you can use polar form, which is typically written as r cis theta. So if you're not familiar with that, I recommend that you watch the videos here in this channel. Let me click here so you can see it. Now the chapter numbers are not correct anymore. No, I'm sorry, this is the wrong one. This is the wrong one, sorry, not that one. That's the preclass. The playlist is here. Welcome to our video series. And the chapter numbers here are incorrect, but you can follow by topic. So the two that are covered this week are Chapter 2, Section 2, Arithmetic with Complex Numbers, and Alternative Representations of Complex Numbers. So let's see. Let's go back here and let me see what I want to say about that. So I think what I'll do is, if you need additional background, you can watch that video to give you the background. What I'll do is I'll do some similar problems to these. I won't do exactly these problems, but I'll do similar ones to give you an idea of how you should go about doing them. So this is from the Abstract Algebra book, 4.2.4. So let's go back there. Should be up. All right. So there's 4.2.5. Okay. All right. So for instance, this first one, and unfortunately it didn't stay there. Let's go there. 4.2.4, 4.2.20, 4.2.13, 4.2.4. Okay. It says here, it says, prove the associative law for multiplication of complex numbers, and follow the style of example 4.2.3. Right. So in 4.2.3, we prove the commutative law. All right. So when you want to prove a law, the best way to do this is start on one side and get to the other side. Right. Now, if we follow through this discussion of commutative law, the left-hand side I can write this way: a plus bi times c plus di. Right. That's the general rectangular form for complex numbers. Commutative law would say that a plus bi times c plus di is equal to c plus di times a plus bi. So start on one side and work your way through, and give a reason for each step. All right. So that's kind of the way you do it. Now I have FLOY here. You may not, probably you've heard of FOIL. I like to use FLOY because when you multiply complex numbers, let me just show that here. Let's go down and do a new page. Okay. Okay. So if I just, where's my pen? Okay, so if I take a plus bi and multiply by c plus di, okay, now the result is going to have a real part and an imaginary part. And of course the imaginary part is going to be multiplied by I. Okay. All right, so how do you get the real part and the imaginary part? Well, the real part actually comes from, one part is from here, You know, if you do this out, I mean, if you did this out by FOIL, you know you would get 4 terms. But here you're taking the first here and the first here. Since these are both real, this is going to give me a real result. Okay. Okay. So that's first, right? Then I'll take the last. If I take the last, I get plus bi times di. And then O is outer, right? So I take O. So O is going to be AD. ADI, now I have the I already set the I out, so that's fine. And then you'll do inner. Okay. And that would be plus BC. Right. So why is this real? Well, you need to use the fact that I squared equals -1. So this is equal to AC plus BD times I squared, but I squared is equal to -1. Okay, so that's equal to AC minus BD for the real part plus AD plus, whoops, AD. It's not doing it for me. Okay, there we go. Plus AD plus BCI. Okay, so that's the formula. Okay, now you could just remember the formula, but I think it's better to remember the rule. Okay. All right, so that's multiplying complex numbers. All right. So now associative law, I hope you know what associative law is. If you don't, you can look it up. I do require some initiative on your part. ChatGPT is your friend, but the law, what you'll do will look similar to this. Give a step and give the reason. Now you can give reasons in more or less detail. You can see here that I don't break it out so much in detail. I say Floyd, and then I say community of real multiplication. You can combine more than one step in more than one reason in one step. Right? But I think it's good to go through the exercise of understanding where these identities come from. Right? And as I said, there should be an answer for this in the answer key. You can check with your work with what's in the answer key. Right? So that's the first question. Second question is 4.2.22. So I jumped quite a bit. You should be able to, I didn't include any of these problems, but you should be able to manipulate complex expressions with actual numbers in them. So these, like this one here, these ones here should not pose a big challenge. Okay? So you might want to practice that yourself. Let's go to 4.2.22. All right. So here we're actually proving general properties. And this is important because when you're doing math, you typically use the general properties rather than writing things out as A plus BI. So even the ones here that you don't prove, you should know. So let me do one that I didn't assign. Why don't I go ahead and do, did I assign I? Right. No, I didn't assign I. So I'm going to do I. So let me get my snipping tool up. And we'll look at this. By the way, jump in. If you have questions, you can jump in anytime. If I'm missing something or something's not clear. So let's copy this. And here, I'll go down here and continue this page. Snip it here. And I think I'm going to do I. Right, where's my pen? Okay. All right, so that's J. Okay, sorry. I was going to do I. Okay. And there are hints in the book. I believe if you click on this, it will take you to the hint. You can verify that. If it doesn't, you can look for the hints at the end of the chapter. Okay. So we have absolute value of Z inverse. Okay. All right. So here when you prove these propositions, if you follow this style, you're actually going to do the a plus bi inverse. Okay, like that. Okay, right. Now there's a formula in the book for this inverse that you can take. Okay, so that's going to be, in fact, what it is, it's a over a squared plus b squared minus bi over a squared plus b squared. Okay, all right. So I can just say this is from the book. Okay. All right. So where do we go from here? I'm just going to put one step on each line now. So if I want the absolute value of this, the absolute value is going to be the real part squared. And again, if you're not familiar with this, you can go back and look at the book and watch the video. It's the real part squared plus the imaginary part squared. Right. Now notice that you're taking the imaginary part. You don't include the I. Both of these terms are going to be positive. Okay. So this is the definition of absolute value. Oh, sorry, that's definition of absolute value squared. So I have to take the square root. Right. Now notice I write 1/2 power instead of the square root sign. Square root signs are very unwieldy. It's better to use powers like square root or fourth root. I know in the algebra packet they use the square root sign. I would definitely convert those to exponents, numerical exponents. Okay, so let's continue here. So if I'm going to do this square, this is going to be a squared over a squared plus b squared squared. Now this is just ordinary algebra with real numbers, right? I'm not using complex numbers anymore. If you use ordinary algebra with real numbers, then you can just say it that way. And then this is going to be plus. If I do the algebra here, I take the square root of the numerator, divide it by the square root of the denominator. Right? Okay. Okay. So this is, I can say, I'll just call that, I'll just call it algebra. Or you can say, actually, what you just say is arithmetic. Well, I guess you call it algebra because you're doing it with variables, so it's just algebra. Okay. All right. Now for more algebra, you just combine they have a common denominator, so it's a squared plus b squared over a squared plus b squared squared. So you could just say algebra or common denominator. Don't be too concerned about the reasons you give. Just give some reasonable expression. Now here you go again. It's 1 over a squared plus b squared, and that's more algebra. Okay, and that's just equal to 1 over the modulus of z, and that's the definition. Whoops! I forgot the square root. I forgot the square root. 1/2, 1/2, and then 1/2. 1/2. Sorry, not squared. 1/2. Okay, and then this is 1/2, and then this is the definition of the modulus of z. Okay, and that's what I wanted to prove. All right. So I know some people start with the entire identity and try to make it true. It's not a good idea. So you can end up giving circular arguments. Start on one side and prove to the other side. Right. And then I think the next two problems, I believe this one, to do the next problem, use the identities in the previous exercise. Even if you didn't prove them, use them. I want you to get used to using identities. All right. So, and then I think I assigned this one also. This one you could use identities, or you can use the a plus bi. All right. So the first topic in abstract algebra is basically manipulation of complex numbers in rectangular form. That's something you should be comfortable with, because when we do the class, we'll go more deeply into the theory. Right. The next part is manipulation of complex numbers in polar form. So polar form, you can read about that. It talks about polar form here. Polar form basically relies on this diagram. Instead of representing the numbers a plus bi, where a is the x value and b is the y value. Let me just snip this also so I can play with that. Where's my snipping tool? Here we are. Okay, let's do this. Here we are. Okay, and then we copy, and then we go here and paste it. Come on, there we go. Okay, make this bigger. Okay, all right. So of course this one is rectangular or Cartesian. That's the rectangular form. And then the polar form is, you write it as r cis theta, or the expanded form is r cos theta plus r sine theta times I. Okay. So these two are equivalent. R cis theta means this. And the relation between r and theta and a plus bi is from trigonometry, right? You draw the triangle here. This is r cos theta. This is r sine theta. So you see the relation there. Now the big advantage of using the polar form is multiplication is very easy, and you can find the formula here for multiplication of complex numbers. And you should be able to convert back and forth also between rectangular and polar form. And here we have what? Where's the... All right, so this is division, which is similar to multiplication, but let me get the formula. Where's the formula? Here we go. The formula's here. R cis theta times S cis phi is R times S times cis of theta plus phi. Okay. All right. So you multiply the moduluses or absolute values, and you add the angles. All right. So that's something you should be familiar with even before the class starts. So that's the algebra content. Now the pre-class content, I'm sorry, the calculus content here. These are all different types of different aspects of algebra that you should know. But just make sure you have that material down. So if we just look at this, for instance, the first one, 10 ACE, let's go there and see that. 10 is, where's A? All right, factoring. Was that the first one? Oh, 147, sorry. Got to go back to 147. All right, simplify. All right. So know your exponent rules. Know how to do this kind of stuff. And find ways to do it more quickly. For example, number 3. Just think about how you do number 3 for a second. Let me get this here. You should be able to not only do these, but do these quickly. You may get tired of my analogy, but I always say you can't play basketball if you can't dribble. Now you're learning. Now this is just dribbling. So you should be able to dribble without thinking. So something like this you should be able to do without making mistakes and without pain. Okay. All right. So find your own way to do this. Now the way I would do it is I would put all the x's together. Like I said, you find your own way to do it. So you can see that there are x's, there are y's, and there's z's. And I would just take them apart. It's all multiplication, so I can pick out the x's, I can pick out the y's, I can pick out the z's. And I can also, and there's also a constant term. So for instance, if I just look for the x's, I have a x to the minus 3 over x to the 5. Here, this one here is going to give me a x to the minus 2. This one here is going to give me an x. All right. So I just put that together to get all my x's. For the y, I got y squared. This y cubed to minus 2. That's something you need to realize. This is not. So you should know your exponent rules. This is not 3 minus 2. It's 3 times minus 2. That's y to the minus 6. Okay. Very important. Don't stumble on your exponent rules. Know those cold. Okay. Divided by y. Okay. I forgot one. Sorry. That's here. Let me go back. I should be more careful. Y squared on the top. Y to the minus 1 on the bottom. And then this one was y to the minus 6. And then this one is y. Okay. Then z, you just have 1 over z to the 0. Okay. And then the constant terms, I have 5. And then I have 2 to the minus 2. Okay. Double check, make sure I got all the x's. You see there's numerator here, denominator here, numerator here, denominator here. Numerator here is x to the minus 3, x to the 5 down here. This one's going to be x to the minus 2. This one's going to be x. I think my x is good. My y squared, denominator, y minus 1. Numerator, y minus 6. Denominator, y. Z, there's only one z. I think I'm good there. 5, and then a 2 to the minus 2. Right? And then you just combine these. Again, exponent rules is the key. X to the minus 3, x to the minus 5, that's going to be x to the 5. Minus 5, sorry. And then this is going to be over x to the 5 times x, so that's x to the 6th. Second one here, then I'm going to have times. This is going to be on the top. Again, I'm adding exponents, y to the minus 4 divided by y minus minus, that's just 1. Okay. And then the z is just, and then this is going to be times 5/4. Okay. So final combination, this here is going to be x. Now remember, when you divide, you subtract exponents. X to the minus 11. This is going to be y times y to the minus 4. And then times 5/4. I'll bring the 5/4 out front. Okay, so that's my way of doing it. Find your own way of doing it, but it should be quick, it should be easy, and it should be accurate. Okay, so I think that 1, 4, and 7 are all different simplifies. So you can see the importance of exponent rules. If you're getting your exponent rules bad, it's going to come back and bite you. Definitely going to come back and bite you. Oh, here's another FOIL. So you should be able to multiply out polynomials. For me, what I do is I look for powers. Since this is a square times a square, it's going to be the 4th power. So I'll find all the 4th power terms, all the 3rd power terms, etc. Other people do it differently. Just make sure you can do it quickly and accurately. Okay. So let's see if we go to 10. 10 is on its suit. All right, come on. Okay. Okay. What is 10? This should be 10 here. Okay, factoring. I mean, there are different kinds of factoring. Make sure that you want to factor out first the common. I mean, the first thing you always do is factor out the common factors, right? You can see there's a common factor of 5. You can see there's a common factor. You want the common factor of x. There's a common factor of x. There's a common factor of y squared. So you want to factor that out and then do other stuff as necessary. All right. So that's factoring. What do we have next? 13, 17, 22. Oh, let's see what we have here. Will it go? Will this work? I guess not. I just have to page down. Sorry. Don't know why I did that. Down, 13, more factoring. Yeah, more factoring. 17, more simplify. Okay, right. Then again, you certainly want to look for common terms. Like here, I can see a W on top. I don't see anything on the bottom yet. But another thing that you need to know is difference of squares. You see this a squared minus x squared? You should know what that is. That's a plus x times a minus x. That's something that should just be automatic. So what else do we have? Let's see, 2022. 20 will simplify. How come it's going back there? 22. Okay, so this also is to put over common denominator, stuff like that. There's also some factoring here. I'm sure that that's going to factor. So bread and butter stuff. 22, 23 CF. Let's see what that is. Okay. More simplification. As I said, please convert the radicals to exponents. This is minus 3 to the 1/3 power. Don't just lose these radical signs. They're a pain. Okay. Right. So 26, and you shouldn't need a calculator for any of this. Shouldn't need a calculator for any of this. This is algebra, not arithmetic. Rationalize the denominator. Technique you should know. What's next? 28. More simplify. Convert the radicals. Next one, 32 and 33. There's 30, 32. All right, so you need to know something about logarithms, right? Let's see, is there another? So I assigned both of these. So if you don't remember logarithms, go back and know that. Now, in this packet, they use ln for natural log and log for log base 10. I'll talk about this more. In mathematics, you just use log for the natural logarithm because the natural log is so much more important than log base 10. So in a mathematics text or mathematics paper, whenever you see log, that means the natural logarithm. But in this packet, because it's geared more to high school or college, beginning college, the log means log base 10. In fact, it's not going to make any difference to the answer in this case, because you're still using the same log rules. Same log rules for natural log as for log base 10. No difference there. This one, though, you'd have, if that's log base 10, then you get a different answer from natural log. Right? So you do need to know something about logarithms. And I think that takes us to the end there. Okay, so next session will be Sunday, and I'll try to get the time right this time. So we'll have it at 7 p.m. again. And the way you access the next one is here on big blue button. You should probably already have received an invitation to this, because I did. So you'll just go here and click on the start button. Okay, that's what I got. Any questions? Anyone still awake?
No questions.
No question.
All right, very good. Well, I appreciate you all joining. And please don't, when I do talk, just feel free to jump right in if there's something not clear. And especially if I forget to share the screen or forget something else. All right, well, this should be fun. If you do have questions, you can email me. I think you all have my school email, thron@tamuct.edu, and we can work this out. It's better to work the bugs out first before the class starts than while it's going on. Okay, well, if that's it, then I'll see you on Sunday. Have a good evening, and looking forward to spending more time with you.
All right.
Thanks, sir. Have a good evening.
Joshua, why don't we just start on so we can rejoin? Is that okay?
Sure, that works.
Okay, let's.
Yeah, that works for me.
Okay, good. I'll hang up and we'll rejoin.